and welcome to Dartmoor Skies at Night episode 2. Our video today is all about supernovas. Now you may have heard something in the news about a supernova recently being detected, so we thought we'd take some time to explain exactly where and when the supernova happened, and also explain exactly what is happening when a star collapses and goes supernova. We'll also explore what will happen when our sun comes to the end of its life, and give you some tips about how to safely observe the sun now. Before we start, a quick heads up that we are planning a live event for 8 PM on Saturday the 13th of June. We'll be covering a few of the things you can look forward to in the coming months in our night skies, the Milky Way, meteor showers, what the planets are up to, and probably some other stuff too, because we do like a bit of a tangent. We'll also be running a Q&A, so you can ask us any astronomy questions that have been puzzling you. All you have to do is join us on our Facebook page, facebook.com/Dartmoor Skies. And if you can't join us live, we will also be sharing the event on YouTube afterwards, but we'd love to have some company, so do join us remotely if you can. Now, on with the vlog.
Thank you, Bryony. So, yeah, a supernova has happened. What does that mean? It means that a star, a large star, larger than our star is our sun, which is out today, which is nice. Yeah, a big star, comes to the end of its life and it essentially blows up. It releases a lot of energy and it's much brighter when it does that than it would normally be. So a star in a galaxy which is called M61, galaxy is 50 or so million light years away. So this explosion happened 50 or so million years ago. It happened somewhere around here, and after the sun sets, we can show you what constellation that is. It's in Leo. You wouldn't usually be able to see a star, an individual star from another galaxy, but because it's so bright from this explosion, we can. All you'll need to see is a large telescope, and it'll be around for a few weeks. So, time yet to catch it. So here's the scene after sunset. The sun has gone down here in the northwest, as it does near the solstice. It goes in near the equinox, it's near the west, and as you get near the summer solstice, it goes further north. So one way of sort of finding where we're starting our little star hop from is as the glow of twilight reduces, there'll still be light coming from the direction that the sun is in, so we'll still be seeing a horizontal glow around here, and you'll be able to pick out the bright star Capella, and you'll be able to hop along to Castor and Pollux, and you can use them as a sort of guide to find your way to Leo, which is a very distinctive sort of trapeze-shaped in the body there, trapeze-shaped constellation. And the galaxy that exploded is in the neighbouring constellation of Virgo. There are an awful lot of galaxies in Virgo. This is the Virgo cluster. Many, many galaxies. So M61 we see there is, if you draw a line between, when I was out trying to find it myself, and between Spica and Denebola, it's about a third of the way from Denebola to Spica. It's a faint galaxy. What's the actual stat on it? Let's find out. Magnitude 9.5. So you're going to need a telescope with an aperture of 10 inches or so to capture this at least. And then the new star happened in one of the spiral arms of this distant galaxy, galaxy 50 million light years away. And if you go constellation hopping, you can, if you don't happen to have a huge telescope, you can still kind of appreciate that somewhere around there a giant star exploded. And I hope that's something you can enjoy.
Supernova come in many different flavours, but 2020 JFO is known as a Type 2 supernova. This is where a massive star, somewhere between 8 to 50 times the size of the Sun, undergoes a gravitational core collapse. Towards the end of these stars' lives, they build up very heavy cores, which are iron-rich, and at some point, the core cannot support its own weight, so it implodes. Now, as it implodes, the outer layers are no longer supported, so also begin to fall inwards, reaching speeds of around 20% of the speed of light, which is quite fast. Now, the core, which is imploding, is suddenly abruptly halted by something known as neutron degeneracy. This is where you sort of squeeze out all the electrons from matter and from the atoms themselves, leaving only the nuclei. At this point, the implosion is halted and the energy is reversed, forming an explosion, which is around 100 million times brighter than the Sun. However, only 1% of the energy is actually converted to visible light. 99% of it is converted to neutrinos. These are tiny particles which we cannot see with the naked eye, but if we could, the supernova would outshine the entire universe. Now, we have actually detected these neutrinos in conjunction with supernova, so we know that the two are linked, and this helps to confirm the theories we have. Now, the outer layers are blown off and these form a nebula, and what remains is the core. The core can either remain as a neutron star, an incredibly dense, sort of small Pluto-sized object, or it may form a black hole. Compared to many stars, the Sun is small, quiet, and quite boring. But for us, this is a really good thing. We're not bathed in high-intensity ultraviolet radiation, battered by solar flares, and if the Sun was similar to supernova 2020 JFO, then the Earth would barely have had enough time to cool before the entire planet was obliterated into a big cloud of gas by that supernova.
So let's have a close look at the supernova. I'm going to make a supernova happen in our solar system so we can get a sense of the scale of what's happening. But as we said, our Sun won't go supernova in a way that the recent one in M61 did, but we're going to create it in our solar system. So I'm going to do that by taking our Sun and making it weigh significantly more than it's supposed to. To make it weigh 15 suns, and as soon as I hit enter here, it's going to blow up. But I've got time pause, so let's unpause time and watch what happens. So as you can see, pretty dramatic brightness difference. It really has lit up, and that's what allows us to see a single star from 50 million light years away. Now, because we were close to real time, the explosion cloud has not got very far at all, even though it's going really fast. You can see there's Mercury that orbits about a third of the distance to the Earth, about a third of the Earth-Sun distance usually, and it's, we can barely see it moving at this rate, so let's speed up time and watch the debris cloud. There it goes. So now at nearly a minute a second. And here's that's all the extra, pretty much all the extra material I put in to make it explode there, coming out again. And it makes a very distinctive, beautiful pattern, which we see in an object, Messier 1, which is a supernova, it's the leftovers of supernova, and it's called the Crab Nebula. But yeah, very distinctive. And at the centre of the explosion, we've got a Sun-nova remnant. So different things can be left behind after supernovas. Some of them are so big that nothing's left behind. Sometimes there's a black hole left behind, or a white dwarf, or other things can be left behind. Just getting out to Mars now. But yeah, hope you enjoyed that supernova demonstration.
The Sun began its life as a large nebula, the leftovers from a supernova similar to that of 2020 JFO. After some time, the nebula began to collapse, forming the star and the solar system around it. This entire period is a time dominated by strong X-rays, fast winds, and very strong magnetic fields. But after about 20 to 30 million years, the star is fully formed and it begins to fuse hydrogen. This is called the main sequence. And the Sun, or stars similar to it, remain on the main sequence for about 10 billion years. So we're halfway through that now. We've been fusing hydrogen for about 5 billion years, and hopefully we'll continue to do so for another 5. Once the Sun has reached an age of around 10 billion years, it will have burnt through the majority of the hydrogen in the core, which is the primary fuel source. So at this point, the Sun will begin to expand. And over the course of around 2 billion years, the Sun will expand to approximately 100 times its original size. En route, it will swallow Mercury, which will be completely vaporized. At this point, the Sun is now a red giant. Now, during the entire time, the core is increasing in temperature, and when the core gets hot enough, it will start to burn the helium there, and something known as a helium flash. This releases lots of energy as the helium is all fused together, and this release of energy blows off the outer layers of the Sun to form a planetary nebula. Now, the core remains and is known as a white dwarf at the centre of this planetary nebula. The white dwarf has no power of its own, no energy source, so it slowly cools over billions and billions of years, potentially until the end of the universe.
So observing the Sun safely, there's a number of different ways to do this, so that you could have specialist equipment. It's actually a fairly cheap pair of modified binoculars, so they've been professionally filtered. Yeah, fairly affordable. You can directly look at the Sun with those, which is unusual. Don't turn everyday binoculars to the Sun. You can also get telescopes that are designed for looking at the Sun, so hydrogen alpha telescopes and stuff. But I'm going to have a look at one of the easier ways to do it today. I've got my pair of binoculars here. It works fine with small binoculars, by the way. These are just the nearest binoculars I had to hand. I'm going to use the binoculars to project the Sun, and I need something to project it onto. I've got a white sheet here. You could use a piece of paper or a wall or anything really. So what we want to do is turn the bigger end of the binoculars, the ends that you don't look in, I want to put that towards the Sun. And if you do this too close to the thing you're projecting onto, you do run the risk of focusing the light and creating heat. So just be aware that you want to have nice generous distance between the two things. And you can use the shadow there to see if you're lining up with the Sun or not. So you'll end up getting the disk, which is there. So you may have to play with the focus a bit, and if you have a second person who might be able to hold the thing you're projecting onto, that would probably be easier. And if you could mount your binoculars on a tripod, that would give you a steadier image too. But it's just a quick example to show you. There's the Sun. So if there were any sunspots, like dark patches on the disk, we would see them with this method, this projection method. At the moment, the Sun doesn't have very much activity on it. Yeah, at the moment the Sun doesn't have very much activity on it because we've been in what's known as solar minimum, so there's not been many eruptions or things going on, so the Sun has looked for the most part like a plain disk. So yeah, do have a go at that. Obviously being cautious, just to reiterate, never look directly at the Sun with your eye or with binoculars or with a telescope, unless it's a special pair of binoculars or a special telescope or a special filter, and you know what you're doing really, because it can be really dangerous. But having a go at the projection method is nice because your eye is not in the optical like train. The light is going through the pair of binoculars onto the thing that you're projecting onto really, so it's safer, with the caveat that you shouldn't be focusing it really close to make that very small point of light we were talking about. So yeah, enjoy.